The question that I have is, could you describe the vector method of finding the moment of a force? Now we know a little bit about the cross product between two vectors and see how we can apply that to find the moment of a force. Say we have a force F in 3 dimension and we are interested in finding the moment of that force about point O. The first step is to take the line of action of F and select a convenient point on the line of action. Alright, so for example, point like point A. So in principle, this point could be anything on that line of action. But we say convenient point because we need to know the coordinates of that point. So you want to pick a point whose coordinates are known. The second thing that you do is you define this vector r as one going from point O to point A. Then the moment of the force F about point O equals r cross F. And of course we can evaluate that using the method we just learned, right? The determinant method, once we know the components of r and components of F. Once we expand this, we're going to end up having a Cartesian vector in its component form like this, right? So there's going to be an x component, y component, and a z component for this moment vector. So this vector has a magnitude and a direction, right? So the direction turns out to be the moment axis. Now let's talk a little bit about the moment about an axis. So far we've been working with 2D problems, right? We've been calling that as a moment about a certain point, let's say point O or something like that, right? But we did make the point that moment about O is actually a moment about an axis that is perpendicular to and coming out of the paper like shown over here. In other words, MO is actually MOZ, which is the moment about the z-axis at point O. In three-dimensional situations, sometimes we want to know the moment about the x-axis or maybe y-axis or maybe even an arbitrarily oriented axis. Say we are interested in finding the moment of this force F about an arbitrary axis like this, and let's call this as the a-axis. So this is what we do. We select a convenient point on that line, alright, so here point O is one of those points, and then we select a convenient point on the line of action of F, and here A is one of those points, and then we define the vector r like we did before, going from point O to point A like shown in this picture. Let's say we have a unit vector along the a-axis, let's call that as UA. Then we first go ahead and find the moment of this force about point O like we did before, right? So we use the cross product for that. R cross F will give me the moment about point O, and this is a vector, right? So once we have that, it turns out that the moment about this axis, a-axis, can be simply found using this dot product like we have done in the case of forces. Now remember, if you wanted to find the projection of a force along an arbitrary axis, all we have to do is to find the dot product between that force and the unit vector along that arbitrary axis. So just like that. So we use the dot product for the moments as well. Dot products are always scalars, right? So the result is a scalar. So now we have a moment about this arbitrary axis. The question is, how do we evaluate MA, the moment about an arbitrary axis, A? Well, there are two ways to do. So let's call this as method 1 and method 2. Method 1, you go ahead and first evaluate MO, the moment about point O, which is a vector, right? So it's going to have 3 components in there. Let's say the unit vector is this, all right? Then simply find the dot product between the two, right? Remember this formula that we talked about before, right? So using that formula, UA dot MO would simply be equal to the sum of the products of the I, J, and K components of the two vectors, right? So it'll be MOX times UAX plus MOY times UAY plus MOZ times UAZ. So it's like a two-step process. First you find MO, and then you find the dot product between the two. But it turns out there's a more straightforward way to do this. So we'll call this as method 2. So what we have here is MA equals UA dot MO, which is UA dot R cross F. Remember, MO equals R cross F, right? So when we do this operation, it turns out that you end up having the determinant of this 3 by 3 matrix. So what's the difference between this and the 3 by 3 matrix we had for R cross F? Well, this first row. Remember, we had I, J, and K on the first row. But here we have UAX and UAY and UAZ on the first row. So there are no vectors here. And therefore, when you evaluate this, you're going to end up with a scalar, just a number. As a special case, let's see how we can find the moment about one of these axes, like x-axis or y-axis or z-axis. So the theory says if we have a unit vector along an axis, all we have to do is to find the dot product between that unit vector and this moment vector, right? Say we are interested in finding the moment about the x-axis. We know the unit vector along the x-axis is little I, right? Therefore, the moment about the x-axis is simply I dot MO, right? But MO is given by this expression over here. So we put that in here, and I'm going to simplify this and see what we get. So what I have done here is I have multiplied through each term by I, and we get this, right? So then we notice that I dot I is 1, I dot j is 0, I dot k is 0. Remember, we just talked about this in one of the earlier slides, right? And therefore, this simply works out to be MOX. In other words, the moment about the x-axis is actually this x component of the moment vector. And I can repeat this in the y and z directions to show that my is actually MOY and mz is actually MOZ. In other words, each of these components that we have in the moment vector is actually the moment about each of these axes respectively. Also note that the positive directions are the ones shown in this picture. In other words, counterclockwise directions about each of these axes are our positive direction for the moments.